What I am about to show is how and what our THZ GPS satellites can do, so hold on to your seat and I recommend you take the red and the blue pill. Level 1, easy and simple. I call it the Anthony level. Our satellites and what they can do are against our constitutional rights. THZ, GPS, rubidium atomic clock, digital optical phase locked loop. Satellite. All of these things come together to make a digital optical phase locked loop. This is an electromagnetic incubator cavity that holds what each one of the items listed above can make. THZ plus rubidium equals T-ray vapor allows terrorists to see into your home. Rubidium vapor from rubidium atomic clock plus 580 nm laser equals thermoplasmonic heating of metalic nanoparticles, or better known as direct energy weapon. This system can also make a quantum optic cloud supercomputer able to hack voting booths in a single bound, not joking. We need this to stop because our military is being trained with this. They then get out and start a very illegal neighborhood watch that makes the person look crazy. Oh, did I mention this weapon creates voice of God, sonic, health attacks and more. Now I added a couple of levels to show the more technical side of this weapon. Blessings to everyone, and this weapon is real. Level 2 explains more about what and how THZ, GPS, rubidium atomic clock, optical frequency comb and digital optical phase locked loop can do and how. I want to ask a question. What do you really know about our GPS system? How it works and what it really does? Think about that for a second. What if I were to tell you it is the basic building block for a quantum optic THZ supercomputer, and can look into your home, also send audio straight to your head so that you and only you could hear it? You would think I was a nutcase. Well, I'm here to tell you it can, and I am going to explain how. I am going to explain how our navigation system works and how it becomes THZ GPS, optical phase locked loop quantum optic computer system that can gather information from your phone computer, look into your home, hear the word you say and inflict phantom pain on your body that does not leave a mark. We do have an upgrade on our GPS satellites now. They are making terahertz THZ GPS satellites. You may not know what THZ are right offhand, but almost everyone has been hit with it. You know them by when you go through a body scanner at the airport. There you go, you've met terahertz frequencies. Terahertz are a compound frequency infrared microwaves that can see almost anywhere. Keep that in the back of your head. Now back to GPS. I know before I found out what it truly is, I thought it was just a sexy lady telling me where to go, but oh no, our GPS is made up of signals. The ones that I will be focusing on are L1 1575.42 MHz, L1 1575.42 is also a GHz and is a microwave signal, and C, a code 1.023 MHz. Let me give you the definition and we will go from there. There are 4 signals available for civilian use. In order of date of introduction, these are L1C, A, L2C, L5 and L1C. L1C, A is also called the legacy signal and is broadcast by all satellites. The other signals are called modernized signals and are not broadcast by all satellites. In addition, there are restricted signals with published frequencies and chip rates but encrypted coding intended to be used only by authorized parties. Some limited use of restricted signals can still be made by civilians without decryption. This is called codeless and semi-codeless access, and is officially supported. Now stay with me because this is where it gets a little yawn. Let's start with the C, A code 1.023 MHz. This is where radio frequencies and IP address can be added and changed into bits and become part of the GPS L1 signal. Yup. Here is a link that explains how it is done. It basically turns your IP address into ones and zeros. Computer talk. Radio frequencies. The radio spectrum is the radio frequency, RF portion of the electromagnetic spectrum. In the United States, regulatory responsibility for the radio spectrum is divided between the Federal Communications Commission, FCC, and the National Telecommunications and Information Administration, NTIA. The FCC, which is an independent regulatory agency, administers spectrum for non-federal use, i.e., state, local government, commercial, private internal business, and personal use, and the NTIA, which is an operating unit of the Department of Commerce, administers spectrum for federal use, e.g., used by the Army, the FAA, and the FBI. Within the FCC, the Office of Engineering and Technology, OET, provides advice on technical and policy issues pertaining to spectrum allocation and use. Frequency can be added to CA code 1.023 MHz-MUTIPLE. Frequencies can be added to CA code using bit code zeros and ones with BPSK modulation method. Then it joins L1 1575.42 MHz, which is a microwave signal carrier which will become part of the optic phase locked loop. https://petri.com/csc_convert_address_from_decimal_to_binary hash:_tilde:text equals here %20 or %20 steps %20 on %20 how comma it's %20 binary %20 form %2c %20 without %20 memorization dot and text equals in %20 order %20 to %20 remember %20 these comma 1 %20x %202 20 3d %202 closing parenthesis. Now that IP address becomes part of the GPS signal and part of the quantum optics computer, and a ping is all that is need to get that information from your computer. Am I starting to get your attention? But wait, we have our other two components to deal with. First, our rubidium atomic clock and optical frequency comb. Asterisk rubidium atomic clock. The rubidium atomic clock provides standard frequency time signal for control over the THZ GPS microwave signal. Will also provide rubidium, soft silver metal, atoms, vapor for T-ray, quantum optics computing, and torture with the addition of a 580 nm laser which creates THERMOPLASMONICS, a form of NANOPLASMONICS. A rubidium standard or rubidium atomic clock is a frequency standard in which a specified hyperfine transition of electrons in rubidium-87 atoms is used to control the output frequency. It is the most inexpensive, compact, and widely produced atomic clock, used to control the frequency of television stations, cell phone base stations, in test equipment, and global navigation satellite systems like GPS. Commercial rubidium clocks are less accurate than cesium atomic clocks, which serve as primary frequency standards, so the rubidium clock is a secondary frequency standard. All commercial rubidium frequency standards operate by disciplining a crystal oscillator to the rubidium hyperfine transition of 6,834,682,610.904 Hz. The intensity of light from a rubidium discharge lamp that reaches a photodetector through a resonance cell will drop by about 0.1% when the rubidium vapor in the resonance cell is exposed to microwave power near the transition frequency. The crystal oscillator is stabilized to the rubidium transition by detecting the light dip while sweeping an RF synthesizer reference to the crystal through the transition frequency. Rubidium, RB, atomic clock, NANOPLASMONICS, used as a weapon on targeted individuals, standard frequency time signal, which provides control of the upcoming phase lock loop, rubidium atoms, RB atoms, protons, electrons, gas, vapor. Asterisk optical N frequency comb, W diode lasers 780 nm signal, 1550 nm probe, C-band, infrared, 1560 nm coupling, C-band infrared, 192 terahertz. In optics, a frequency comb is a laser source whose spectrum consists of a series of discrete, equally spaced frequency lines. Frequency combs can be generated by a number of mechanisms, including periodic modulation, in amplitude and/or phase, of a continuous wave laser, four-wave mixing in nonlinear media, or stabilization of the pulse train generated by a mode-locked laser. These together create an optical phase locked loop, which is a cavity that supports a controllable, navigational, targeting system, called a THZ quantum optics computer, that can send and receive information anywhere in the world. Now make sure you check my research that I have done while being tortured for 9 years. Open your minds, check my research, and above all remember this is happening all over the world. It is torture. Let's begin. GPS plus rubidium atomic clock, rubidium vapor plus optical frequency comb equals optical phase locked loop filled with rubidium vapor and terahertz frequency, which is infrared and microwave. The optical phase locked loop is put around its target home, building, voting booth. Rubidium atoms are pumped into the phase locked loop. Phase-locked loop is an electromagnetic loop which causes the Zeeman effect, keeping rubidium atoms, vapor in line and trap in the GPS-controlled cavity. 1550 nm probe and 1560 nm coupling laser cause Doppler cooling, which is when lasers lower the speed of the atoms, optics down. A signal, laser 780 nm is introduced, causing electrical induced transparency, getting proton, electron cleared to absorb information and transfer it to 1550 nm infrared probe, C-band and or 1560 nm 192.114 THz, C-band infrared. Keep in mind all of these things can be added or produced with our GPS satellites. When a ping, computer hacking, is sent and received, all information can be taken live or recorded onto C-band and shared. This is the birth and incubator of a THZ quantum optics GPS rubidium supercomputer. Ping is used to gain access to any GPS or satellite equipment in vehicle, and it can be used on any electronics in the optic phase locked loop. Let that set in. Pinging a new known and unknown host port and IP address will generate DNS packets. For any new known and unknown host port and IP address, it will generate at least 2 packets like request and reply model, and a maximum 27 packets we can generate per ping request. Now the information is ready to be shared via satellite or 5G. Image this phase locked loop over an electronic voting station. Computers speak in ones and zeros called bit code. Person puts bit code information into C, A code 1.023 MHZ, which then goes to L1 1575.42, becomes part of the phase locked loop. Radio frequency over fiber, laser ROF, also becoming a part of a quantum optics computer with the ability to hack whatever is in the phase locked loop. Electronic voting booths. Need I remind everyone this system is what was attacking our American diplomats? The cricket noise. Please stay with me, it gets better. THZ GPS, rubidium atomic clock, optic frequency comb, able to put optical phase locked loop around a home, voting booth, building. All of these things can be produced from a THZ GPS satellite and are responsible for 3 main weapon systems that are created with this quantum optics THZ GPS, rubidium, quantum optics computer. 1. Sonic, health attacks. 2. Weapons used on targeted individuals. 3. Voter tampering. This is my findings from almost 10 years of torture with no help. Bye. Optical phase locked loop, terahertz GPS, radio frequencies, THZ 192 frequency can see into homes, rubidium atomic clock, soft metal, metal nanoparticles, RB vapor, first half of components needed for THERMOPLASMONIC torture, and quantum optic computing. Optical frequency comb. Needed for quantum optic computing, 580 nm, 780 nm adjustable diode laser, 1550 nm probe laser C-band infrared, 1560 nm coupling laser C-band infrared frequency 192 THz. These produce cavity and mobility of this phase locked loop. GPS containment of quantum optics supercomputer. https://u2.be/cpqx1acback. I can prove this exists and how it works. THZ quantum optics, electronic harassment, sonic, health attacks, weapons used against targeted individuals and voter tampering are at their core made from our GPS, rubidium atomic clock, optics frequency comb, all made in an optical phase locked loop. I did it. I solved this shit. Terahertz GPS, rubidium, soft metal, atomic clock equals optical phase locked loop, OPLL. Rubidium nanoparticles contained in a GPS, rubidium, optical frequency comb, optical phase locked loop plus 582 nm diode laser equals THERMOPLASMONIC. Look this word up, also known as electronic harassment. THZ plus rubidium nanoparticles in the OPLL equals T-ray body scanner. https://www.rp-photonics.com/terahertz_radiation.html. Imaging and communication from optical phase locked loop created by THZ GPS, rubidium atomic clock, optical frequency comb. This is the cause of electronic harassment, voice of God. https://www.jins.com/americas/applications/optics-photonics/optical-phase-lock-loops. Optical phase locked loops. The incubator, womb for a terahertz quantum optics computing. Produced by Terahertz GPS satellite. Divisions. Terahertz GPS, rubidium atomic clock, optical frequency comb. One of the many things produced from optical phase locked loop is this. This goes by many different names. Voice of God, V2K voice to skull, sonic, health attacks. I will also explain how the cricket noise of an optical phase locked loop. First definition, abstract, an optical phase lock loop, OPLL, is a feedback control system that allows the phase stabilization of a laser to a reference laser with absolute but adjustable frequency offset. Now remember, with radio over fiber, these lasers have radio frequencies around them. Structure and function of an optical phase locked loop. Phase detector, low-pass filter, voltage-controlled oscillator, and feedback path, which may include a frequency divider. The voltage-controlled oscillator increases and decreases the DC current. The higher the current, the higher the frequency, and the lower the current, the lower the frequency. Here is a video link. https://youtube.be/kgshhjgvjgq. This is used for torture. I will explain how a person can hear this coming up. Inside of this optical phase locked loop, OPLL, are microwaves from carrier signals and terahertz and more, which are contained in an electromagnetic optical phase locked loop, EOPLL, which can be controlled with GPS and rubidium atomic clock, standard frequency time signal. Check my research. When the EOPLL is put around a target, that target is saturated with microwaves, and this causes the frontal lobe of the brain and the cochlea to swell, letting radio frequencies bypass the ear canal and eardrum, bouncing off the cochlea and onto the frontal lobe, producing sound like a cochlea implant. This is called microwave auditory effect hearing. The radio frequencies are added to the CA code 1.023 MHz on the GPS, becoming 1, then moves to be joined with L1 1575.42 MHz and sent out to be wrapped around the frequency comb lasers. This is called radio frequencies over fiber. Now remember, the EOPLL is made up of all of this, so consider it a dome of radio frequencies for now. The added frequencies can now be dialed up with SDR, radio phones, or any two-way radio like a police would use, and more than one frequency can be attached to the equals multiple audio signals, hearing voices, harassment, terrorists. Microwave auditory effect hearing. Sonic health attacks are brought on the same way, but what is heard here are the superposition beat frequencies. The cricket noise basically hear multiple frequencies of different lengths. Remember, our GPS is the cause of electronic harassment, sonic health attacks, and voter fraud. https://www.jins.com/americas/applications/optics-photonics/optical-phase-lock-loops. Optical phase locked loops. The incubator, womb for a terahertz quantum optics computing. Produced by Terahertz GPS satellite. Divisions. Terahertz GPS, rubidium atomic clock, optical frequency comb. Whistleblowing. Terahertz satellites can see into anyone's home or private property. https://purview.live.mil/2018/12/next-generation-of-satellite-communication/. The rabbit hole runs deep. GPS plus rubidium atomic clock plus optical frequency comb equals optical phase locked loop equals containment for THZ quantum optics supercomputer. New terahertz satellites plus rubidium atomic clock equals T-ray airport security T-ray. This is how a directional energy weapon is made with American satellites. NANOPLASMONICS thermoplasmonic. When a target person is in a phase locked loop, they are covered in rubidium, soft metal, able to become a vapor, nanoparticles. When nanoparticles are hit with a 582 nm diode laser, they create what is called thermoplasmonic effect. This equals a DO weapon. American family tortured by ex-military personnel, Army. This weapon is used to produce sonic health attacks, voter fraud, weapons used on targeted individuals, remote computer hacking. These things listed below are produced by one system that we use every day. Computer hacking capabilities: ping, changing frequencies in a rubidium atom-filled optical phase locked loop. Diode laser 780 nm, 1550 nm, 1560 nm. C-band, share info anywhere in the world. Infrared. Terahertz sees through walls. Rubidium, soft metal, atoms, vapors, highly volatile with water. Zeeman effect. Radio frequency over fiber, laser, ROF. Voice to skull. Microwave auditory effect hearing. Doppler cooling. Gray molasses. A.V. remote wireless vapor surveillance torture. Want to know what and how? It is responsible for sonic, health attacks, weapons used on targeted individuals, and voter fraud. Take some time and get to really know America's GPS. Definition of radio frequency. Any of the electromagnetic wave frequencies that lie in the range extending from below 3 kHz to about 300 GHz and that include the frequencies used for communication signals, as for radio and television broadcasting and cell phone and satellite transmissions, or radar signals. Many remotes, garage door openers and other things can be manipulated if radio frequencies are matched. Most of these radio freq can be utilized and manipulated live in the EOPLL. What frequencies do voter booths run off of? Ping. Frequencies can be added to C, A code 1.023 MHz. Multiple frequencies can be added to C, A code using bit code zeros and ones with BPSK modulation method. Then it joins L1 1575.42 MHz, which is a microwave signal carrier which will become part of the optic phase locked loop. Rubidium atomic clock. Optical frequency comb. NANOPLASMONICS thermoplasmonic. Alkali metal vapors, rubidium-87, enable access to single electron systems, suitable for demonstrating fundamental light-matter interactions and promising for quantum logic operations, storage and sensing. Here, we use plasmonic nanoparticles to convert light into localized thermal energy and to achieve optical depths in warm vapors. This is the DO weapon used on targeted individuals. The items listed above can work as generator and/or satellites, and most of the time a combination of both to add, subtract items. With all of my tortured research, I have found that the most important part to this system is the optical phase locked loop. It is an electromagnetic field, dome, cavity. This system encapsulates its target with 3D surveillance and torture. Funny how water only seems to be the only real firm of protection, and everyone claims tin and metals stop TI attacks. It is a metal, electromagnetic system, huh? All of these three systems working together and pack a punch. Level 3 technical difficult. A fibered laser system for the MEGA large-scale atom interferometer. D. O. Cebulski, J. Junka, and B. Canuel. Abstract. We describe the realization and characterization of a compact, autonomous fiber laser system that produces the optical frequencies required for laser cooling, trapping, manipulation, and detection of 87 Rb atoms, a typical atomic species for emerging quantum technologies. This device, a customized laser system from the Muquans company, is designed for use in the challenging operating environment of the Laboratoire Souterrain Bob Brouet, LSBB, in France, where a new large-scale atom interferometer is being constructed underground, the MEGA antenna. The mobile bench comprises 4 frequency agile C-band telecom diode lasers that are frequency doubled to 780 nm after passing through high-power fiber amplifiers. The first laser is frequency stabilized on a saturated absorption signal via lock-in amplification, which serves as an optical frequency reference for the other 3 lasers via optical phase locked loops. Power and polarization stability are maintained through a series of custom, flexible micro-optic splitter combiners that contain polarization optics, acousto-optic modulators, and shutters. Here, we show how the laser system is designed, showcasing qualities such as reliability, stability, remote control, and flexibility, while maintaining the qualities of laboratory equipment. We characterize the laser system by measuring the power, polarization, and frequency stability. We conclude with a demonstration using a cold atom source from the MEGA project and show that this laser system fulfills all requirements for the realization of the antenna. Subject terms: micro-optics, techniques and instrumentation, optics and photonics, fiber lasers, semiconductor lasers, atomic and molecular physics, matter waves and particle beams. Introduction. Large research infrastructures require the production of customized, well-engineered equipment to meet demanding scientific requirements, and for use in environmental conditions that often goes beyond standard laboratory ones. Such requirements stand at the frontier of industrial and laboratory-grade qualities. These devices need to be stable, remote-controlled, and have the possibility of mass production while maintaining flexibility and high performance. The Matter Wave Laser-Based Interferometer Gravitation Antenna, MEGA-1, is a large scientific instrument presently under construction at the Laboratoire Souterrain Bob Brouet, LSBB-2 in Rustrel, France. MEGA is based on an array of atom interferometers simultaneously manipulated by a resonant light field circulating in a 150 m optical cavity, creating a state-of-the-art gradiometer. This antenna will be the first underground infrastructure dedicated for matter wave experimentation. It will pave the way towards the realization of a new class of gravitational wave detectors in the infrasound domain 3 and enable to study gravity gradient fluctuations at low frequency 4. This large-scale antenna requires dedicated, automated instrumentation subsystems to make the infrastructure cost-effective and simple to maintain while accomplishing scientific goals. One of the most challenging of these subsystems is the laser apparatus to control the numerous atomic sources within the antenna. These devices must comply with environmental and technical requirements that differ significantly from those of typical laboratory applications. The environment within the underground LSBB laboratory is challenging, with galleries located at a depth up to 500 m below a karstic massif, where the system must operate remotely and stably without frequent maintenance. These constraints necessitate a fiber optical solution. Telecommunications C-band equipment is reliable, well-tested, and has demonstrated ability to work under non-laboratory conditions. Critically, this solution does not need constant maintenance. The laser system must also be able to meet the requirements of a complex, modern cold atom system. It needs to cool atomic clouds launched from the atomic source to a 3D kinetic temperature in the range of a few μK, in a single magnetic substate, and in a narrow range of velocities along the axis of the laser interferometer. It is also required to provide all laser frequencies needed for a detection system based on fluorescence. This laser system, based on reliable telecommunications technology, has applications toward mobile, field-deployable quantum technologies. Pioneering experiments in matter wave interferometry 5 to 7 demonstrating inertial sensitivity led to significant interest for precision measurements using atomic beamlines. Development of laser cooling schemes 8 to 11 during the last 30 years have produced a series of methods to produce small 3D kinetic temperatures in dilute atomic gases. This led to atom interferometry with cold atoms, which has a track record of accuracy and precision spanning the development of laser cooling. This technique has been used to measure gravity 12 to 17, gravity gradients 18, 19, rotations 20 to 25, measurements of the gravitational constant G26, 27, determination of the fine structure constant coupled with tests of quantum electrodynamics 28, 29, studies of the interface between gravity and quantum mechanics 30, 31, general relativity tests such as the searches for violations of the weak equivalence principle 32 to 38, tests of local Lorentz invariance of post-Newtonian gravity 39, experiments in microgravity 40 to 42, tests of dark energy 43, 44, and recoil associated with blackbody radiation 45. Based on this record of precision measurements, cold atom interferometry gained traction as a candidate system for observing gravitational waves at low frequency 46 to 52. The schemes developed in these experiments form a core technology under the auspice of emerging quantum technologies. As a new type of deployable sensor, atom interferometry is being applied to inertial navigation 53 to 55, space and satellite missions 56 to 59, mineral prospecting 60, 61, and civil engineering 62. These applications require, and have led to, the development of reliable, stable, mobile, and compact laser systems to control, manipulate, and measure the atomic samples under varying environmental conditions. These devices have increasingly relied upon frequency doubling of stable C-band telecommunications lasers and the related developments to make such lasers rugged and reliable 63 to 72. Mukwon 73, the first company to bring to market a completely fibered laser apparatus dedicated to cold atom production and atom interferometry 74, has been selected as the commercial entity to realize the automated fiber laser systems for the MEGA antenna. In this report, we present the first realization and characterization of such a system, designed for the MEGA project. We demonstrate that this device fulfills its application requirements from measurements on a prototype atomic source of the antenna. First, we present a series of schematic diagrams of the laser system and discuss its internal subsystems. We then report on the performance of the device, measuring the stability of polarization extinction ratio per output intensity and frequency. Finally, we test the laser by applying it to the cooling, launching, and preparing of clouds of dilute 87 Rb, which requires all the functionalities of the laser system working in concert. The laser system for MEGA. The core technologies of the autonomous fiber laser system are a result of advances in C-band telecommunications devices. All lasers in the system comply with Telcordia qualification GR46875. These external cavity diode lasers, ECDLs, are routinely offered with line widths 10 kHz at 1S and optical powers of 10 MW in a compact butterfly package. We use lasers tuned to 1560 nm, which when frequency doubled through a periodically poled lithium niobate PPLN crystal to 780 nm, are capable of cooling, trapping, and manipulating atomic rubidium. Our application requires significant power after frequency doubling. C-band telecommunications technology offers high power, low noise, fiber optic solutions for applications requiring powers in excess of 100 MW in the form of erbium-doped fiber amplifiers, EDFAs. Combined with significant improvements to and cost reductions of polarization, maintaining portable, stable micro-optic benches, complex configurations are easily realized. 76. The MEGA project laser system is a combination of these advances: a fibered, compact, autonomous plug-and-play racked system, in Fig. 1. It can be completely remote controlled through a terminal interface via Ethernet. This connection allows communication with the laser as well as monitoring of the various subsystems. The system is contained within a climate-controlled, mobile rack. The climate control of the rack creates a mobile laboratory standard environment. This allows the laser system to operate at the LSBB unimpeded by local temperature and humidity. The temperature within the LSBB facility is around 15 degrees C with humidity that can reach almost 100% depending on venting conditions inside the galleries. When the rack is closed for operation, the climate control system operates a heater and fan which is able to increase the temperature inside up to 10 degrees C with respect to the ambient environment. This brings the temperature up to that of a typical ambient laboratory and prevents condensation. The laser system has the dimensions 117 cm 80 cm 55 cm, requires 100-240 VAC at 50 to 60 Hz for 300 W max power, and weighs 150 kg. Figure 1. The automated laser system inside of a typical mobile 19-in rack without thermal condensation shroud. There are 8 2U and 3U rack units with the following functions: from bottom to top, the power supply converting 230 VAC to various DC. Design principle. The system is based on 4 fibered ECDLs, primary oscillators that are frequency stabilized. The first is a reference laser, which is used by the other 3 oscillators as a fixed frequency set point. These other 3 oscillators, CDDFAs, we refer to these primary oscillators as seed lasers. They are labeled as the 2D-Mo seed, the 3D-Mo, Raman 2 seed, and the Repump, Raman 1 seed, and are frequency stabilized to address various transitions in the 87 RBD2 spectrum. 77, enabling the laser cooling of 87 Rb atoms in a 2D 3D-Mo configuration and to realize Raman spectroscopy, CP, of Fig. 1. The aforementioned seed lasers are frequency agile, in that their frequency can be shifted by 1 GHz in less than 1 ms, which is useful for reducing the number of seed lasers required to run the system but also to operate in an interleaved measurement configuration 2578. In this way, we can realize both cooling in the 3D-Mo and Raman transitions with the same pair of seeds 3D-Mo, Raman 2 and Repump, Raman 1, by changing their frequency set point. To control these lasers and the system peripherals, we designed the control inputs of the system to match a homemade control system. 79. We cascade the control systems, enabling the control of many lasers through a single remote interface. The tests reported in the present paper were carried out with this dedicated control system, but we emphasize that any computer control system that has analog and digital outputs can operate the laser. Laser architecture. The complete laser architecture can be seen in Fig 2 and is composed of 4 lasers, 4 amplifiers, 4 PPLN doubling crystals, 1 electro-optic modulator, EOM, 5 acousto-optic modulators, AOMs, and 6 different micro-optic benches. One of the 4 primary oscillators, the reference laser, is frequency stabilized to the largest spectroscopic crossover feature in the 85 RB spectrum by lock-in amplification on saturated absorption spectroscopy. This spectroscopy cell is around a few cm in length and is encased in a magnetic shield. The other 3 are frequency stabilized via beat notes to this reference with optical phase lock loops, OPLLs. These oscillators seed EDFAs, which in turn seed fibered PPLN crystals. The line widths of all lasers were measured to be less than 40 kHz at 1 second, at 780 nm. Figure 2. Schematic of the laser system. Each primary oscillator passes light through a fibered optical isolator and into a combination of fused fiber splitter combiners to create beat notes. The 3 primary oscillators that are frequency stabilized via beat notes. The laser system is clocked with a 100 MHz input. This is used to synchronize the DDS that controls the various laser beat notes in a phase-locked dielectric resonant oscillator PLDRO. We create microwaves near to the 87 RB hyperfine frequency by mixing controllable DDS signals with the 3.5 GHz PLDRO and then employing multipliers. Frequencies in the range of 70 MHz are generated directly by DDS and are mixed and multiplied. High-frequency beat notes are fed into the OPLLs where they are divided down and then mixed with the control frequencies. The lasers can be frequency modulated by their servos, up to 200 kHz using their current. The servos have a slow path that feeds back in the diode temperature up to 0.5 Hz. The 2D MO seed passes light through an inline electro-optic modulator, EOM, to illuminate the F equals 1 manifold before undergoing amplification and frequency doubling, CB, in Figs 1 and 2.2. The 3D MO requires the 2 seeds, 3D MO, Raman 2 and Repump, Raman 1, the former for the cooling transition and the latter to pump atoms out of the dark manifold F equals 1. By applying a frequency jump, the seed lasers driving the 3D MO can also drive Raman transitions. There are 4 EDFAs in the system, 1 for the 2D MO seed, 1 for the Repump, Raman 1 seed, and 2 for the 3D MO, Raman 2 seed. This last laser has its amplified output split among multiple micro-optic modules. Each amplifier seeds a fiber-coupled PPLN crystal, doubling the optical frequency from 1560 nm to 780 nm. The PPLN conversion efficiencies range from 40% W to 60% W depending upon the input power at 1560 nm. We typically use 1 to 2 W of power at 1560 nm. To maximize this efficiency, we use an automated scan that varies the temperature of the crystal to find and set the phase matching temperature. The outputs of the PPLN crystals inject custom-built micro-optic splitter combiner modules, CFIGs 2 and in 3.3. The Raman beams pass through AOMs before frequency doubling while the cooling transition frequencies pass through integrated AOMs within the micro-optic modules after doubling. For this reason, the Raman EDFAs have a higher output power to make up for significant insertion loss through the fiber AOMs. We employ 6 micro-optic modules in this laser system to distribute the laser frequencies into 14 polarization maintaining PM fiber optic outputs. There are 3 outputs for the 2D MO, for the horizontal, vertical, and push beams, C outputs 1, 2, 3, on Fig 3. There are 6 outputs for the 3D MO, C 4, 2, 9, 2 outputs for Raman beams, C 11, and 12, 2 outputs for the detection frequencies, C 10, and 14, and 1 output for a beam used to clear the F equals 1 manifold of the 5S12 ground state, C 13. Figure 3. Schematic of all micro-optic splitter combiners employed in the laser system, a 1-3 micro-optic splitter with an internal shutter before splitting, to shutter all beams simultaneously. This is used to split the 2D MO light B1. The laser system presented here is an entirely commercial device that can be adapted to atom interferometer experiments using atomic rubidium, as well as potassium-80 and cesium-81. These systems can be made more mobile and compact 74 for applications outside the laboratory. With the addition of micro-optic modules, they gain adaptability. This commercial product and the constituent laser, RF, and micro-optic technologies are the legacy of the pioneering experiments performed on mobile atom interferometers 54, 80, 82 to 85. Seeking to utilize rugged, reliable technology, we settled on C-band technology based on its previous use by mobile atom interferometer experiments 80. This allows for the use of superior polarization maintenance technology, the ability to utilize low-noise, high-power C-band optical amplifiers with a cleaner spectrum than is available at 780 nm, and, due to optical frequency doubling, better extinction ratios and a reduction in RF complexity of frequency stabilization and manipulation 80. The C-band lasers typically employed by mobile laser systems are compact, reliable, traceable, and fiber-coupled. These ECDLs typically demonstrate a line width 1 to 2 orders of magnitude smaller than distributed Bragg reflector (DBR) and distributed feedback (DFB) laser diodes at the same wavelength. DBR and DFB devices are the nearest competing rugged and mobile technology, which provide high power that can preclude the use of a tapered amplifier, are similarly vibration insensitive, and are compact 84, 85. Among different solutions available for splitting and combining light 82, 86, 87, we opted to use monolithic bases of Inver Fe36. The laser architecture presented here is then the latest development in applying C-band telecommunications technology to laser cooling and trapping, in which we try to address the issues highlighted by these other methods and meet our application requirements for the MEGA equipment. Micro-optic modules. After frequency doubling, the output of the PPLN crystals has to be distributed among a number of PM optical fibers with differing amounts of power. This can be done using fused fiber optic beam splitter combiners or discrete optical systems contained within ultra-stable modules. At 1560 nm, we employ fused fiber splitters for making beat notes, seeding amplifiers, and within the amplifiers themselves, CFIG2, as these devices have a proven track record of reliability, stability, and ruggedness in telecom and space applications at this frequency. At 780 nm, polarization maintenance of fused fiber devices is less reliable, especially in challenging environmental conditions. After frequency doubling, we employ miniaturized free space polarization optics to split and combine laser light at 780 nm. These micro-optic devices, manufactured by Kylea 76 for Muquans, preserve alignment and polarization in compact, hermetically sealed modules, CFIG. 3. This option is flexible because we can easily change power outputs, and it allows an easy translation from complex optical bench setups to miniaturized, mobile bench designs. The ability to tune the outputs is a major advantage, allowing the fine-tuning of each laser system for all atomic sources. These devices have a typical insertion loss between 1.30 dB and 1.50 dB for each input. Every module has internal photodiodes to monitor the input light temperature, sensors to correlate output power drifts, and a linear polarizer in front of every input and output to ensure maximal stability. Typical modules weigh 1 to 2 kg with dimensions 100 mm, 250 mm, 50 mm. In Table 1 we present measurements of the performance obtained for each fiber output of all splitters, the maximum output power, the minimum polarization extinction ratio over 3 hours, and the RMS power noise over 70 hours. The optical layout of the micro-optic modules is translated directly from optical table configurations. Table 1. Mean output power, MW per dB, over 3 hours, and the RMS power stability over 70 hours of the 2D MO module can be seen on a Fig. 3. The frequency doubled output of the PPLN crystal is injected into the module input, first going through a linear polarizer and then a small beam sampler for monitoring. After passing through a blade-type shutter, the beam power is divided among the 3 outputs using half-wave plates and polarizing beam splitting PBS cubes. The 3D MO light is divided into 6 outputs through 3 micro-optic modules, CFIG2 as well as C, D, and E of Fig. 3. The 780 nm light from the PPLN enters the micro-optic module, E through a linear polarizer and beam sampler for monitoring. The light, after power splitting through the polarization optics, is sent through single-pass AOMs, shutters, and is re-injected into fiber optic to be sent to the next splitting modules, C and D. These two modules, used to create the 3D MO beams, are similar to the 2D MO module, the only difference being that the module C for the bottom three beams of the 3D MO has a second injected frequency, the repump light. The Raman light is directly injected into the module from 2 ppLN crystals, C-Fig2 as well as F of Fig3. We opt to use AOMs at 1560 nm because they provide a higher extinction ratio, which is preferable for the application of driving Raman transitions, despite the significant optical insertion loss. The module F combines, in the same polarization, the two frequencies required for driving a Raman transition into two optical fibers. Raman 1 and Raman 2 are combined into a single beam and are split between two fibers, Raman up 11 and Raman down 12. A modest beam pickoff from Raman 1 is sent from module F to module B. This module creates the repump light sent to the 3D MO module C, but also the outputs 13 and 14, used for preparation and detection. All power outputs are variable. They can be modified by simply opening the module and rotating the waveplates. The alignment and stability are maintained, despite the lasers being shipped various times and moved around their host facilities. The ability to finely tune the modules is necessary for pairing the laser to an individual atomic source, in order to meet sensor head performance requirements. Laser frequency stabilization. Frequency stabilization is crucial to laser cooling, trapping, and manipulation of neutral atoms. The required stability is small by comparison to the line width of the transition in 87 RB, 6.07 MHz. Frequency error of the 2D MO seed and 3D MO, Raman 2 seed directly corresponds to quadratic changes in the spring constant of the respective traps. Frequency error for the preparation or detection leads to incorrect velocity selection or error in atom number counting. To this end, the reference must be stable at the hundreds of kHz level at long times, and this frequency stability must be passed on to the other seed lasers. The reference laser signal is split and mixed with samples of the 2D MO seed and the 3D MO, Raman 2 seed using a series of fused fiber splitters, C-Fig2. These bead notes are used to servo the frequencies of these seed lasers via OPLLs 88, 89. The fourth laser, repump, Raman 1 seed, is phase locked to the 3D MO, Raman 2 seed. In this way, all seed lasers have similar stability to the reference laser. The frequency chains used to control these lasers are presented on the left of Fig2. We exert control over the laser frequencies using DDS in combination with a series of RF multipliers, dividers, and mixers. In this way, we can use RF frequencies 200 MHz to control bead notes up to 7 GHz with precision and accuracy to the sub-Hz level. For direct manipulation of GHz frequencies, we mix in a 3.5 GHz signal from a PLDRO. It is phase locked to an external 100 MHz signal provided by the user, typically an ovenized quartz oscillator or atomic vapor clock, itself referenced to a disciplined GPS signal. These signals are converted into error signals and fed into a phase lock, creating a closed-loop frequency stabilization with an agile set point that the user controls. Remote control and required system inputs. The laser system requires a series of user inputs in the form of TTLs, control voltages, and sinusoidal waveforms in the MHz range to function. We employ a custom, application-specific control system designed within the MEGA Project 79. The user communicates with the laser system via SSH or Telnet connection through terminal from any computer. The laser system has a series of internal computers for acquiring diagnostic data, controlling the amplifiers and PPLNs, and frequency stabilizing the lasers. The diagnostic information about the laser system includes temperature of each rack unit and critical components within each of them, set points for currents and voltages, live-lock loop parameters, and photodiode monitoring at 1560 nm and 780 nm from the seeds to the amplifiers and after the PPLN crystals in each micro-optic module. These diagnostics are sampled at 1 Hz for remote monitoring, but can be increased up to 100 Hz. Analog connections are available for higher bandwidth data acquisition. The laser system provides a flexible control of the Raman transitions. The Raman power is controlled by using dedicated RF attenuators which change the RF power sent to the AOMs, C-Fig2. The frequency is controlled by changing the applied RF signal that sets the lock point of the Raman lasers, see Fig. 2. Techniques like adiabatic rapid passage, ARP, block elevators 72, and stimulated Raman adiabatic passage, STIRAP, are possible with the setup presented here or with small modifications. Laser characterization. Here, we characterize the laser system performance by testing its outputs. We start by investigating the polarization stability of critical outputs. This study leads to a discussion of the power stability, followed by frequency stability from the reference laser and an estimation of its frequency accuracy. All tests in this section have been performed in a typical laboratory environment, i.e. temperature and humidity. Polarization stability. Polarization stability is critical to our application in two ways. First, in our optical configuration, it directly translates to power instability, and so atom number fluctuation. Second, polarization error of the Raman beams used in preparation and detection leads to inefficient pulses and unwanted light shifts. To this end, we characterize the polarization stability by measuring the PER over time. We report the minimum PER for each laser output over 3 hours in Table 1, i.e. the worst PER obtained over the complete time series. These tests are of the entire optical path required to get to the output of the fiber. These tests consisted of periodically stressing the fibers and measuring the worst PER. In Fig. 4, we also present a time series of the PER of the Raman fibers, 11 and 12, as an example as our most sensitive application. We find that, for over 3 hours, the dominant fluctuation is thermal. The data sets shown are characteristic of the PER, shown up to 1380 S for clarity. We find that all output fibers exhibit a minimum PER of 20 dB, and for the Raman outputs, we find a minimum PER of 25 dB. Figure 4. PER of the Raman fibers, a PER of the two frequencies required to drive a Raman transition through the first Raman beam path fiber, 11. Green is omega 1, whose minimum PER is 29.8 dB, and blue is omega 2, whose minimum PER is 25.4 dB PER. Power stability. The laser system must maintain both short and long-term power stability. The power stability of the system is controlled by two independent feedback loops. The first is a servo on the output power of the EDFA at 1560 nm. The second is a servo for the PPLN crystal temperature. The doubling efficiency is typically a broad feature as a function of temperature and can be the source of power drift at long times. We servo the temperature of the crystal. We have the option to servo the temperature of the crystal on the output power at 780 nm from a monitor photodiode. We measured the laser power over time, sampling at 1 Hz to observe any fluctuations in their characteristic time. We present the maximum output power and RMS of each output in Table 1. We present some of these data, see Fig. 5 for critical outputs as overlapping Allen deviations, ADEV, relative to the output power level. Figure 5. Overlapping Allen deviation of laser power stability, normalized to output power, at detection frequencies. Different total beam paths through the micro-optic modules lead to different power drifts, B3D Mo, up versus down. In a Fig. 5, we compare the power stability of the detection frequencies, the light from the cooling laser and the repump laser used to detect atoms. In B, we compare a fiber from the trio of 3D Mo up beams to a fiber from the trio of 3D Mo down. In C and D of Fig. 5, we compare the two laser frequencies that comprise the light in the fibers, 11 and 12, the Raman fibers. These power drifts are small, being a few parts in 10-3 on short timescales, less than 100 S, and 10-2 on longer timescales, 104 to 105 S, which satisfies our requirements. This performance is comparable to and in some cases better than contemporary systems 70 to 72. If this performance needs to be improved, sufficient access to the AOMs is given to operate each AOM in an intensity noise eater configuration. In Fig. 6, we show the same output of B in Fig. 5, but as a ratio to the output of all fibers from the same micro-optic module. This is a test of the stability through the micro-optic modules. This is also an accurate estimate of the best performance an intensity noise eater could obtain, as the power fluctuations presented here are no longer common mode. We find that power drifts between the outputs of the splitters are of the order of 10-5 at short times, 70s, and around 10-3 at 104 to 105s. Figure 6. Overlapping Allen deviation of laser power stability as a ratio to total fiber output in a micro-optic module, normalized to total output power. Shown for the up and down fibers, we observe similar behavior at short frequency stability and estimated accuracy. The laser system has an optical reference frequency, the reference laser in Fig. 2, using lock-in detection to the largest spectroscopic dip in a rubidium spectrum with a natural abundance of the isotopes, the 3 to 4 crossover in 85 Rb, and on the D2 line. To this end, we split the output from the reference laser in 2, at 1560 nm. The first path is frequency doubled to 780 nm and injected into a saturated absorption spectrometer 90, which in turn feeds a lock-in amplifier to servo the laser temperature and current. The second path is split between two mixers with two seed lasers for the creation of beat notes. Closing this servo loop creates a frequency reference with low drift and reduced environmental dependence. We use a heterodyne technique to measure the absolute frequency stability of this reference signal using a beat note with an external reference laser, shown in a Fig. 7. This external signal is obtained by first using a seed frequency stabilized to the same dip in the rubidium spectrum and then using a seed laser that is frequency stabilized to this external reference laser such that the beat note between the seed and the reference laser is close to 80 MHz. We make a beat note between the reference laser in the laser system and the 80 MHz offset seed laser from the external reference system. We monitor the frequency difference of this beat note and an 80 MHz reference signal using a frequency counter. The related data are presented in Fig. 7. In B of Fig. 7, we show a 25-hour test of this frequency difference sampled once every 10 seconds. We observe a minor trend, a low-frequency liftoff at times greater than 4/104s. In C of Fig. 7, we show the overlapping Allen deviation of these data relative to the optical frequency. We find the frequency stability to be better than 510-11 at 10s and better than a few parts in 10-10 at 2/104s. Double y-axis shows the ADEV relative to the frequency of the transition 384.23048446855 62 THz77 and relative to the set point KHZ. The frequency reference for the 80 MHz offset is an ovenized quartz oscillator without GPS disciplining. This may be responsible for the drift at long times. Our device displays typical performance 64, 67 to 69 of a saturated absorption spectrometer and its lock-in detector. Better performances can be achieved using more complex techniques such as modulation transfer spectroscopy 91. Figure 7. Schematic and test of the reference seed frequency stability test versus an external reference laser. We compare our reference seed laser with a separate, external reference laser, pictured here, through an offset beat node. This external reference tests using an atomic source of the MEGA antenna. To conclude our characterization of the laser system, we attach it to an atomic source, an exact model of the cold atom source that is used on the MEGA Project 1. In brief, a horizontal 2D MO loads a 6-beam 3D MO. The atoms are launched, cooled, and then pass through a preparation region where the atoms undergo a velocity preselection along the horizontal direction parallel to the interrogation laser. During this, they are also loaded into a magnetically insensitive substrate of ground states. They enter the interferometer interrogation region. Afterwards, they fall back into this preparation region to be detected via fluorescence. Details of the design and performance of the atomic source are not the subject of this paper. Here, we present only the atomic measurements required to ascertain that the laser system meets the MEGA project requirements. More details on the atomic source are available 92 to 95. We measure a loading rate in excess of 3.7109 atoms/s from the 2D MO to the 3D MO, C, of Fig. 8. After loading, we launch the atoms vertically at 4m/s on a ballistic trajectory to reach an apogee of 85 cm above the 3D MO. For the following tests, we load the atoms into the F=2 manifold where they populate the 5 Zeeman sublevels almost equally. We use red detuned Sisyphus cooling after the launch to bring the atomic ensemble's 3D kinetic temperature down. In B of Fig. 8, we show a temperature measurement of the ensemble. We use a long, velocity-selective Raman transition in a counter-propagating configuration to observe the Doppler-sensitive delta MF equals 0 transition, measuring a temperature of 2.3 μ K along the axis of the beam. Following this examination, we perform counter-propagating Raman spectroscopy, scanning a larger frequency range to observe co-propagating and Doppler-sensitive transitions, as well as observe the Zeeman splitting of all features, see Fig. 9. For the data of this last figure, we load the 3D MO from the 2D MO for 100 ms. The Raman lasers have a detuning delta equals -1.36 GHz, see B, in Fig. 1. We scan delta, with respect to the hyperfine splitting of 6.834 GHz. We minimize the light shift by setting an intensity ratio of Raman 2, Raman 1 equals 1.896. We use a constant intensity pi pulse, that is square in time, with a duration of 94 µs. This is in a Gaussian beam with a 1e2 waist of 19.5 mm using low power 20 MW. We use a counter-propagating configuration. Our frequencies come over the slow axis of the fiber, Lin-Lin input polarization, and are rotated by a lambda, 4-wave plate at the retro-reflection mirror. This allows us to see both plus or minus Kepler Doppler features. The beams are tilted down with gravity by 5 degrees to observe the Doppler-sensitive transitions. We apply a nominal 40 μt magnetic field parallel to the beam path. Without clearing any of the Zeeman sublevels, we see features corresponding to all possible delta MF equals 0 transitions. We expect the atoms to be equally distributed among the Zeeman sublevels of the F equals 2 state, with variations in this distribution due to non-adiabatic turn-off of the Sisyphus process in the polarization gradient cooling, slight power differences in the 3D MO beams that lead to occurrences of optical pumping, and/or inhomogeneous magnetic fields and gradients through the region of cooling. We find all expected properties, and that these spectroscopic features display a slight inhomogeneity in the normalized height of the features. Using these data, we determine the applied magnetic field empirically to be 38.5 μt. We do not find unexplained scalar, vector, or tensor light shifts. Having observed Raman spectroscopy of the F equals 2 manifold, we conclude that we can manipulate the atoms using Raman transitions with this laser system. We do not use this laser system for atom interferometry with Raman transitions. The MEGA project creates individual atom interferometers through Bragg diffraction, which is generated separately from this laser system. While not intended to interrogate an atom interferometer, this laser system has demonstrated the ability to make interference fringes 95. Figure 8. 3D MO loading rate and temperature determination, a loading rate of the 3D MO. At 1 second, we measure 3.7109 atoms. The initial loading rate is 8.0109 atoms. B. Temperature determination after. Figure 9. Counter-propagating Raman spectroscopy, after cooling and launching atoms in the F equals 2 manifold, with an applied magnetic field. We scan the 3 MHz around the hyperfine splitting, 6.834 GHz, symmetrically. We use a pi pulse width. Following this test, we measure the atom number stability as a function of time. We perform this test for over 4 days, see of Fig. 10. We analyze the fluctuations and present the overlapping Allen deviation normalized to the mean number of atoms, with the minimum and maximum extent displayed. These data were taken using the same sequence as the spectroscopy test. With these findings, we conclude that the laser successfully integrates with our prototype and meets the application requirements for the cooling, trapping, manipulation, and detection of 87 RB. Figure 10. Atom number stability, atom number fluctuations over time. B. Overlapping Allen deviation of the number of atoms, normalized to the mean number of atoms. The red shaded region and thin red lines show the minimum and maximum extent. We observe a turning. Conclusion. We have designed and tested a laser system intended for the use of quantum technologies in a research infrastructure operating in a challenging environment. Here, we present tests of the polarization, power, and frequency stability for this device over a long time. Owing to the architecture and use of dedicated micro-optic modules, the system exhibits performances that meet the stringent requirements of the MEGA project. Using a prototype of the MEGA atomic source, we show that the system can cool, trap, manipulate, and detect 87 Rb atoms. All tests reported here were carried out in a laboratory environment. For the purpose of a benchmark, the laser system has a thermal management system to create a mobile laboratory environment, ensuring its operation in varying conditions in terms of temperature and humidity. This will enable the system to operate within the underground LSBB facility. Owing to the use of the industrial standard of fiber C-band telecommunications equipment, this system is reliable, flexible, and suitable for mass production. There have been a total of 5 laser systems of this type produced for the MEGA project, all of which show comparable performance thanks to these technological choices. Developing an industrial laser system that meets the requirements of cold atom physics is critical to the success of large-scale atom interferometer projects such as MIGA-1, ZAIGA-51, ELGAR-52, VLBAI-97, MAGIS, AION-98-100 and other national initiatives for atom interferometry presently under construction and consideration. These large-scale atom interferometers seek to utilize different atomic species. The laser system shown here can be modified for potassium-80 and cesium-81, with work ongoing for alkaline earth species such as strontium-101. Furthermore, this laser system is an industrial asset for the production and operation of 87 Rb quantum sensors. This device is easily miniaturized from this facility scale form factor and, as such, is featured in mobile gravimeters, atomic clocks, and magnetometers. Acknowledgements. This work was realized with the financial support of the French state through the Agence Nationale de la Recherche (ANR), within the framework of the Investissement d'Avenir programs Equipex MEGA, ANR 11 EQPX0028, and IDEX Bordeaux, LAPHIA, ANR 10IDEX03-02. This work was also supported by the Région d'Aquitaine, Project IASIG 3D and USOFF. We also acknowledge support from the CPERLSBB 2020 project, funded by the Région PACA, the Département du Vaucluse, and the FEDER PA 000321 Programmation 2014-2020. We acknowledge the financial support from Ville de Paris Project HSCNSMWGRAV and Agence Nationale pour la Recherche Project PMI ANR 18CE47-0002-01. GL thanks DGA for financial support. XZ thanks the China Scholarships Council, number 201,806,010,364 program for financial support. JJ thanks Association Nationale de la Recherche et de la Technologie for financial support, number 2018-1565. Author contributions. The conception of the laser architecture and primary tests were done by BB, AL, and PB. The laser system was designed by AB, GS, AL, BD, PB, and BC. The system was built and tested by GS, JS, and BD. The manuscript was written by DS and BC. The laser data were analyzed by DS, JJ, GS, and BC. The tests of the laser system on the MEGA cold atom source were carried out by DS, JJ, GL, XZ, AB, MP, QB, RG, AL, PB, and BC. The atomic data were analyzed by DS, JJ, and BC. All the authors contributed to manuscript preparation, as well as having read and approved the final manuscript.